Good morning, good afternoon, good evening to everyone. Welcome to the second part of the Machining Stainless Steel and High-Temp Alloys webinar with our presenter, Mike Sperake. My name is Isabel. I'm from the marketing team, and as always, I want to welcome you to another webinar. And if it's the first time you join, I want to tell you that this is another training from our plan to teach and train the metal cutting community, because we organize around 2 or 3 trainings and events a month, and these will help increase your machining knowledge. They have helped our customers and partners to choose the best solutions and in the end to make customers happy. As always, I want to tell you that safety is one of our top priorities. So if you are at home, if you are in your car or in the office, make sure that you are in a safe place and also that you are following any rules and regulations if you do have any. The presentation today will last around 45 minutes. Mike, as prepared as usual, a great presentation. I think he has really included this time many success stories, also a few videos, and he's going to focus mainly on hole making and turning today. And at the end of the webinar, you will also be able to ask questions, but if you have any questions throughout the webinar, write them in the chat so you don't forget them. And at the end of the webinar, we have a survey, and the surveys are important for us to understand your needs and evaluate our next trainings. So I will leave it to Mike, and I wish you a great training.
Thank you very much. Yeah, I hope everybody can hear me. Thank you very much, Isabel, for introducing. Yeah, I hope also that everybody's in a safe place and it's been really aware about the Corona rules and everything we have to follow. So very challenging time, but so I'm even more glad that that you all can join us today, and hope we can have a very nice, interesting hour. Feel free really to ask questions. It's really mandatory that I also get some feedback to our content, because for sure we are going to improve that, and we want really to make you happy about the webinar, and that you like to join it. Yeah, first of all, yeah, I hope you can see now my screen. Isabel, can you confirm?
Yes, Mike, we can see your screen now.
Very good, very good. So what we want to speak today again about stainless steel and high-temp alloys. You know, as you already joined, you're expecting that we give you some answers about the challenges what we have with these kind of materials to machine. And as we already started the last time with indexable milling, solid carbide end mills, but I think not everybody this time who joined was also seeing the first part of it. I would like to spend also some time to make a small introduction of what we are, where we are, and why we have really some experience with stainless and high-temp alloys. Yeah, just bring that to the point. I mean, it's starting a little bit with a name. In Germany, you know, WIDIA, if you say, especially with the older people, they already know what WIDIA means. So a lot of people associate that really with carbide, and still, especially here in the region of where I am, with the Ruhrgebiet area, a lot of people know the history about WIDIA, and for sure also connected the history of Krupp. And the interesting thing, and this is from the marketing perspective a very nice name. So we are really lucky to have this kind of name today, because it really means our core product, like carbide, like diamond, which is meant by hard, really hard like diamond, really for very good material for machining processes. And we started pretty early to work on that because we are already starting in 1925 really to introduce production processes to produce carbide in the nowadays form. So the basic technology, how carbide is made, the reception is for sure not really changing the last more than 90 years. But for sure, in detail, the processes are for sure much more optimized today. And that is a very important thing to understand, that we are really one of the ones who really work for more than 90 years on these kind of products. And our former mother, and you see a small sign here already on my picture, hope you can read it. It's meant Krupp. That is our old mother who started with WIDIA. They were introducing stainless steel in the common nowadays used form. So as steel production, Krupp was really one of the companies who introduced these kind of materials. They were very experienced in material science. They also working a lot in other materials from already before, and that is one of our core competencies. So that's the reason we are speaking a little bit also about the applications where it's coming from. Yeah, if we are already at the history side, we started in 1925, as I already said, to produce carbide, introduce the name WIDIA for it. And then also we for sure interrupted a little bit through the Second World War. We are really making very good progress, and as we already increase also globally, we also were one of the first companies who are starting really in India to really bring the economy a little bit ahead. That's also a very important step. That's also the reason that we are still have the plant in India, and we are still have a huge place there where we produce carbide, where we produce tools, also not only for the local market today, as it was planned in the beginning. For sure, we are using that also with our global resources. Coming a little bit more to global resources, for sure, WIDIA is now a company or a brand which combines more products as only the WIDIA former products from Krupp history and the stuff we did in India. As we are now nowadays part of the Kennametal company, we have access to many technologies, and we are pretty glad about that. That we have really really good products in our portfolio, which covers a lot of needs. That's the reason we separate that at least in two parts for hole making and turning, as well as for the milling section. Really not to have it too long to really introduce all the technologies, because there's a lot to be considered about it. Yeah. Yeah, the next step was also for sure when we look into the future, and you are already aware about that, the industry next generation will be connected everywhere. You know, digitally connected means really to have a very nice idea how to really be more effective in the future. And we released also a software tool already in 2014, which helps us really to improve also there, which is a perfect connection between really the machine, the environment, what we have, the CAD/CAM solution, the warehouse, the measuring systems, and all of that. We have a very nice piece also developed what we can use there, and we can really push really to get you also on that level very easily. Yeah, also 2016 for sure, we have then 90 years. If you calculate from 1925 and 2016, 90 years, we introduced the name in the end of the year 1925. The production starts in 1926. So there the 90 years are coming from, means also we are now this year 95 years, which is one of the oldest companies who are doing really tooling. And for sure, WIDIA with cemented carbide, we are really the first ones who can really have that products. Yeah, as I said already, we are for sure nowadays globally in a global network. Also, we do have plants not only in Germany, as you have seen already the picture before from Essen. This plant is still existing. We are using that for sure, although the buildings are pretty old meanwhile, but still we are producing a lot of tooling there, mainly inserts coming from Essen. But we also have facilities in India, as already said. We have also a facility in America, what we share with the friends from Kennametal for sure. We have also a plant what we can be used in Israel. We have also a plant in Vietnam. And if you think about Vietnam, you might think, well, this is a third world country, and nothing's coming from there. Why we do have a plant there? I can tell you, the first world products are coming also from Vietnam. So if we look at our biggest customer in Vietnam, that's the main reason that we have a plant down there, is making mobile phones. It's a Korean company, maybe you know it, Samsung. Yeah? So it's also been in Vietnam. They produce their stainless steel housings of their mobile phones down there, because they are not going to China, and so that's the reason that we also have a plant in Vietnam. Yeah, that's a little bit about history. Speaking a little bit what we want to speak about today. For sure, I will repeat a little bit the situation with stainless steels and the challenges about it, and high-temp alloys, and why they are pretty much relatives from our perspective, because the challenges which are been solved or needs to be solved in stainless steels and high-temp alloys are yeah, they are not the same, but the way to go is the idea behind what is the challenge is pretty similar, and so it makes sense to combine that and speak about both material groups a little bit, because also there's a mixture sometimes. You know, it's not clearly separated at M. It's something completely different than S, because the content of the material is very important to understand. For sure, what we as a producer for cutting tools can do to help really to improve the applications, that is for sure a very important part. And for sure, I will show you which kind of products would be ideally perfect, where we spend our energy and our R&D resources in the last 90 years, really to optimize really these kind of processes to bring you on a higher level on productivity. And this is for sure about the ISO turning. We are speaking about grooving and cutoff platforms, and I'm speaking also about indexable drilling. The reason is not to speak about solid carbide drilling, because indexable drilling is pretty much relative also to the way of machining to turning. It's closer to turning, although for sure you create a hole. That's for sure the difference. But if you think about axial turning, you are pretty close to indexable drilling, and that's the reason I thought it's a good idea to really include that here in that presentation and webinar. Yeah, for sure, the biggest challenge you need to think about really of the machining process, and if you really look what's really important for the machining process, you need to first have a look on the material, what needs to machined. And there are a lot of physical, mechanical, and manufacturing properties which are important for understanding how to machine these kind of materials. That's about tensile strength for sure. The hardness plays a big role. The ductility, the heat behavior, the abrasiveness, and the machinability. Reason is for all of that really to understand, if you machine here, you create a chip here, you see it in that picture, and for sure you create heat. And you know, every material has some limits, and it might change because of the heat influence. And that's very interesting and important to understand what kind of influence you have, and where the heat is going to, and how you can control about all of that. That's the reason you have to really look very deeply in the workpiece materials and understand that's really also about these kind of properties where it's really been necessary to look at. this manufacturing property about machinability is a very helpful thing, because it sorts out really which kind of material seems to be very relative, but in the end you understand very fast how to adapt really cutting data or the right tooling for it, because they are specific in a very challenging situation sometimes. Also, it's on the first point of view not really looking at it. So it's very good. This machinability, what the engineers were creating, is really an interesting indicator really to do the right things. Yeah, what are the most challenging thing in these kind of materials we are talking today? It's a content of the alloys, and basically the most challenging alloys which really get us on problems if you are thinking from steel machining. It's first of all chrome, which is usually in high temps as well as in stainless steels, because that's the most important part of it, which gives you really the stainless property of the material. And then additionally, you find also nickel and titan in it. This is very nice if you have these kind of alloy components in the materials, but it's really pretty challenging then for machining. And if I speak from the past, some materials are really not easy to machine, and our fathers and grandfathers would say you can never machine it. But nowadays we can machine it because we understood much more how we do that, and that's possible nowadays. Yeah, speaking a little bit about these machining, the classic, the coefficients, we were doing in the last 90 years a lot of engineering and research work really to understand which kind of properties are in the materials, also because our mother companies, and not only WIDIA, also the group friends, and also the friends from ATI Steram, where we also have a very good connection in, are really looking very deeply in the materials, as they also produce these kind of materials. So it's very interesting. We have pretty much success and access to these kind of people. So we know pretty much a lot of about the structure of these kind of materials and how to machine it. It's for us not a secret, and we save that for sure in a huge database, really to make it easy to handle it. And basically that is the source where Novo gets also the information from. And we have already in our database, and this is the old slide, I can tell you, that might be much more nowadays. We had already at that time 770 different high temp alloys and stainless steels, only these kind of materials. No aluminiums, no cast irons, no standard steels. These are very just the unique ones, you know, and this is pretty interesting. So we have a lot of experience and access to these kind of knowledge, and we know really how to machine it. Yeah, coming first of all to stainless steel, and the classical two different portions of stainless steel are separated in V2A and V4A, which are old group names for the stainless steel materials. V2A means really that is a test material 2A, and V4A is the one which is resisting to more corrosion, especially from chloride, salt water, swimming pools, chemical industry, where you have really these bigger challenges. These were the two core products where everything started with in the beginning of last century, and that's a very interesting thing. And for sure, the naming today is a little bit challenging because every country has designed his own norms and his own naming. So it's not easy for a customer or for you as a person who is applying these kind of tools and understanding the properties of the materials to understand which kind of material is in front of you, because it makes a big difference if you have, for instance, here 14301, which is the international description, compared to 14305, because the 05 is a very easy to machine material. 01 is pretty challenging to machine. So it's really yeah, it's really necessary to look really deeply in the materials. The old German description gave you in the past a lot of information about the content, about how much chrome is it, how much nickel is it. So I like this old style classification, because with the numbers you have to well search first of all in databases what is in, and that's a little bit for sure take you longer time to understand the material properties. Yeah, and V4A, which is really the austenitic challenges getting even more on track, is really, if you look here in that, the first one was 14571, which is called in American IC norm 316 Ti. So it's alloyed with titanium, which is not really nice for machining. And in old documentations, you find really the sentence, you cannot machine that. You can weld it, you can put that together, but you're not able to machine it. And therefore, I said it's very interesting how to machine it, because nowadays we can machine it. That's really historic information. Yeah, just looking a little bit detailed, how we have in our database these kind of information available, where I can look which kind of coefficients we can use for that. Also, you see here a lot of names, because for sure a lot of companies are introducing a little bit different reception, or maybe reduced tolerances. All of that is not really telling you, if you see these names, the properties. And so it's really key really to trying to understand that. But most of the producers of these kind of materials are giving information meanwhile in the internet, so you can find the properties pretty easily. And then you can understand how much, well, if I have a lot of nickel or titanium in the material, then it's getting even more challenging, and maybe I need to reduce even more speed rate, or you can have same feed rate, or you need to adjust it somehow. That's pretty crucial then really to understand. Yeah, that's about the stainless steels. The same is if we go to the next level, which are the super alloys, heat resistant alloys. They are mainly based on these kind of materials, which are on the stainless materials, an alloy component. But the most important heat resistant alloys are for sure the nickel based and the titanium alloys. And therefore the base material is not steel, it's really the nickel or the titanium. And that gives you a lot of properties what you really would like in the usage of the workpiece. If you think about nickel-based alloys are very heat resistant, so if you have exhaust systems or turbine blades or stuff like that, that's very helpful if you have the material is staying stable under very high temperatures, compared to for instance steel or titanium. And titanium is giving you the situation that you have really very corrosion resistant material, which is pretty light, but in the same time stable like steel. So it gives you a lot of properties where the people who are looking at the weight of the material and needs of the tensions and the forces been taken from the material are very lucky about it. So we find it for sure a lot in these kind of weight critical applications like planes, or even the Formula One cars. You find a lot of titanium, so it's pretty interesting really to look at that material as well. But titanium itself, and not only titanium, chromium as well, has a well, a challenging effect. It's called ductility, and ductility is really defined as the ability to withstand deformation without breakage. That sounds pretty technical, but you can just think about of a gummy situation. So it springs back a little bit, and additionally, it really creates a very heat problem. And that these two really challenging things are getting really you when you're trying to machine it really to a challenging situation. And the same a little bit, but not in this high amount really with chromium. And therefore I said, well, that's pretty close relatives to it. But nowadays we can, with the modern complex geometries, we can really work on that, and it's nowadays possible to really machine it pretty effective. But basically also, especially in turning and indexable drilling, it's important to understand that you have basically very long chips if you have a high ductility. So it means if it's getting gummy, you get really problems to have short chips. And if you're really then trying to evacuate the chips from your machining zone, then you always get problems, because it's like a very long spring. If you have that around in your machine, it's never helpful, and it also maybe have a high risk of hurting the person who's operating the machine. Yeah? So it's very important to work really in the direction to get short chips, and yeah, and therefore I will show you later which kind of geometries we are using for that. Yeah, next step is for sure also to understand the heat. As on steel, for instance, a lot of heat volume is going into the chip itself, so you can easily have the chips moving away from the cutting zone. So the heat is taken off additionally with the chip itself. The problem is, especially when you look at titanium and nickel-based alloys, but also on chrome-based or chrome influence, you see that less heat volume is going in the chip. Means to end up really in high speed and feed rate is not possible, because then the heat is going to the insert or to the workpiece, and both is not really helpful, because if it's in the workpiece, it deflects, and if it's in the cutting tool, maybe the cutting tool was been heated up too much, and yeah, then you get again a huge problem. Yeah, at least it's really looking on the machinability and the tool life. Yeah, what can we do really to influence these kind of situations? For sure, we can work with the substrate, means the carbide itself. We can work with the coating, which is on nearly every tool nowadays implemented. But for sure, also the biggest steps we made the last centuries, I guess, with the macro geometry. So we can really think about how we break the chips, how we can really control the chips, how we can make the contact zone for the chip smaller. This is all possible nowadays with the modern geometries, and for sure to have a very precise and good micro geometry is very helpful. Though the edge prep really to control cutting forces, and for sure also the surface quality. Yeah, coming to the solutions, if we look at grades, means the combination of the substrate, the carbide, and the coating on it. If there's really a difference, because as we were just speaking about the stainless materials, usually you're using CVD coated. That's a special process how we coat our inserts with a very thick coating on it, and so we have 3 different grades where we can mainly use them. That's WM grades, and when you joined last time, I explained also a little bit the naming about it. So M is coming from the material here. 15 is the ISO hardness of it. So it's pretty easy to understand. This is a very hard grade, and that's a medium grade. It's 35 is a tough grade. C stands for CVD coating. P stands for PVD coating. Because it's not always that everything just from the catalog gives you all the performance you need. Very often you come to the point you have to say, well, I have to do something different, and then you come to the situation that you even are not really managed all the heat, because maybe the coolant is not good enough from the machine. Maybe the situation where you need to machine the workpiece is not possible to get really coolant too, and therefore it makes sense sometimes to look at the maybe higher heat resistant grades, means the S grades, where we have the choice between the WS10 PT, P for PVD coating, and the WS25 PT, really to understand that we have here alternatives also in this kind of arena to choose. Yeah, coming a little bit to the coating, what we are using. Basically, the M coatings are just differences into the thickness and the number of layers. It's always a multi-layer coating what we are using, these kind of grades. Nowadays, also the biggest steps the last years were made really in post-coat treatments and really good surface qualities. And for sure, also aluminium layer are very important because they are preventing really heat very good from the insert. So means if I get heat really to the insert, you can increase the speed already, because they're better isolated between the insert, which is on the geometry for sure touching the insert, and taking really heat into the insert and bringing heat to the situation, which is for sure somewhere a limit. Yeah, this is the basic idea about the CVD grades. The main ideas which kind of insert geometries can be used for stainless steels. The first choice inserts are starting always with a U in our portfolio for stainless. Means UF for fine machining, UM for medium machining, UR for roughing, and sometimes it's also possible to use a RH geometry, even if the situation gets more challenging and chip breaking and chip control is less a big problem. Even two life and really high loads are more important, then RH also can be used in these kind of stainless materials. You see already that's the pressed in designation of the insert. That, for instance, is an 0.8 corner radius. Here in the two, it's the designation for the US guys in inch. And you see also, if you have the insert in your hand, you even do not need to understand the geometry itself by the naming with the UF, F for fine, medium, and roughing. Also, it's been possible that you go with the classical symbols for fine machining, for medium machining, or for roughing here in that way to understand the insert. For sure, between those, you need to understand for sure this is a more insert for really for having more protected against the heat, and this is for more really to have higher loads on it. Yeah, this is the basic idea of the first choice of it, but for sure there are a lot of geometries what you also can use in case of. Yeah, you come sometimes to limits, and then we have a lot of different alternative geometries where we can really use them. And sometimes, you know, also you find older designations like the number designation, but it gives you an indication what kind of materials been used. In the catalogs, you find it pretty easy to really use these kind of geometries, because for sure we trying to help you also in catalogs and also for sure in Novo to find out which would be the one you need to focus on from your kind of application point of view. And you see these kind of windows for the feed rates. This is UM, UF, UR windows here. You can see that easily. Here's the feed rate in millimeter. Here's the depth of cut in millimeter. The similar thing we have for sure for the inch sizes. But it gives you for sure the same idea. And you see these in windows, and you also can see where you are already with depth of cut, and here with the right geometry do that. So the same for grades. This is the one, if we look at the positive single-sided inserts, for sure we have some additional geometries there, the fine and the medium positive inserts. So you see we try to use a naming which you can recognize easily. If you're trying to remember it, that F stands always for fine, so will be the finishing insert. The P for the positive one in that case. So we have here a very easy, simple, understandable naming system. Yeah, let's dig a little bit deeper in the geometries itself. We have the UF geometry, really dedicated for stainless material, and you see already we have here several chip breakers in it to really control the thin and springy chips, which are really giving us problems in that. And that's the reason we designed these kind of inserts, that we really have the chip control completely here in these kind of areas, and make sure that we can have short chips, and we really optimize this kind of geometry in long testing rows, really to make sure that we have a good solution here on hand. The same for geometry, means a more stabilized cutting edge. Less the problem that you have a chip breaking situation, because if the chip is getting thicker, it breaks easier. Yeah, because then if you bound it, it's important to bound it pretty good. But then if you have a very fine geometry here, then it wouldn't be helpful in that case. Let's go a little bit through the UR geometry. This is for sure the geometry which helps a lot for roughing, and you see a lot of geometry features here in it, and I need to explain that a little bit more, because they all make sense. They are not by random just on the insert. Really, we have chip breakers here on the land, really to make sure that we maybe can bound it also in that way to make sure that it's breaking. We have protecting steps also to make sure that we don't have so much long contact with this wharf with the insert. And we can also make sure that we can have coolant below the chip, so we can also cool down from that side already, and make somehow as a cushion below the swarf, really to cool it down, to avoid contact zone, not to heat up the insert, and really make sure that we have a longer tool life with that, and for sure also with higher speed capabilities. If we look at the positive side, MP geometry has similar ideas. Yeah, so you see also here chip breaking elements on it, and chip bounding elements, really to make sure that we can really to get a control about the chip. And the same for the finishing insert, but very often you need really less geometry of these kind of inserts. Yeah, showing a little bit how how results against competition are looking like. We had here several nice samples and examples where we really show the competition. I don't use the naming of the competition. I don't name them by the company or the brand. But sometimes you can see a little bit about the great naming, and then you can understand which kind of competitors is behind. Just for your understanding, we increased here massively the tool life from 7 to 13 pieces by that application, just by using the same cutting data. I know customers don't like to change cutting data, although they're always asking for more tool life. And the operator, I can understand them. They don't want to have more time for maybe have really the correct timing on it. I see here a comment, and that's a very nice one, and you are pretty right. TP 2500 is not for stainless steel, but you know, I cannot change the mistakes of the customer or the competitors. I just can give them the right solution. And if the customer takes the wrong insert and complain about it and ask me what to do, I just can tell them, well, look, I can give you the correct solution to it and can improve your tool life, and maybe also your performance. That's a very important point on it. Yeah, looking here on a duplex F51 material, also that was pre-machined, we can increase here really cutting data. Yeah, means we increase speed rate, go a little bit down with the feed rate, but we can increase really the tool life with really from 15 to 25 pieces, which the customer does like. And it's always a little bit the question also, what kind of thing you want to update and what is necessary at the customers. So you have to react on this kind of communication on it. Yeah, another example, it's a 316 stainless steel, that means 144 4 material. This is also dedicated with the RH geometry, which is very interesting. You know, as I said earlier, we can use on a really high load on it. We can use the RH geometry, and that's a 90 mil insert, and we are going with 8 millimeters depth of cut, and with a feed rate of 0.45, and can increase the speed to 90 meters here. So makes sense to really have an improved situation, and so the customer is buying these kind of inserts for their application. Another example, really, with 144/04 material, based on our UR geometry. Again, nothing was changed here, and we just can increase our tool life, because also that is really showing up in a very good performance. Yeah, I just don't want to show you also only pictures. I just want to show you a video. This video, you won't hear any sound, I must tell you before. It's very important to understand you can also download these kind of videos or use them also at customers, or have for your own reference. Look at our WIDIA YouTube channel. We are officially showing these kind of videos, and gives us a good indication of what can be used where, and have really a nice overview of it. Yeah? So we are seeing here really a nice assortment of geometries, and not only really the 100% correct from the book right geometry of assortment. Look, that is our actual UR geometry on stainless 4301. The geometry also, that's really for the depth of cut of 3 mil, 180 meters, feed rate of 0.35 is not bad. That's really good, and we have really here a high performance. The medium roughing MR is coming more or less from the steel, but you see also that is working. These kind of inserts, so it's not always really the secret just to use it only from the catalog. Also, you need to understand the material challenge, and also for sure the customer needs. Depth of cut 6 millimeter, 160 meters, 0.5 feed rate, and here the RH geometry with the same cutting data. Also there we have a short chipping, so it's a very good process, pretty visible on it. Yeah, let's take the next step, going to the high heat resistant super alloys. The grades what we propose there, first of all, for sure, the carbide grades, like WS10 PT, the coated one with PVD, and WS25 PT. But for sure, we have also an uncoated grade, as some machines don't need these kind of need of sometimes of a very low speed, but you then sometimes need a very sharp cutting edge. Then this kind of insert is helpful. And if you really go to extreme high cutting speeds, then for sure we have also the possibility to change to a ceramics insert like CW3020 or even PCBN. So we can also super finishing here these kind of materials. It's always dedicated to the application in detail. Yeah. Just an overview, nickel-based alloys can be really machined with PCBN grade or ceramics, and for the titanium grade we have also the choice that we can use PCD for finishing. Yeah. Jump back a little bit to the PVD coated grades. Also, that's a multi-layer coating, very specific for these kind of materials, with alumina layers included, very strong insert. But for sure, also we have here, especially for the high-temp alloys, two geometries which can be chosen really by the guy who needs to applicate that. For sure, we have the medium for high temp alloys called MS, and we have the FS geometry, but also I recommend really to look really deeper in the application, and sometimes it makes sense to really change to another kind of geometry from the portfolio of the stainless steel inserts. So it's easy to understand then really that the challenge is coming from somewhere else. There's coming a question. This is pretty interesting. It's heading a little bit to the stainless steel grades we showed before. He's asking why we are using a P grade, so a grade for steels in stainless material. Sometimes, you know, it makes sense if the situation needs to do these kind of applications, that you have to rethink what you already identified, because the challenge is somehow different. Means maybe the machine needs to take more load, or the speed cannot be improved because it's already on the limits, and therefore it sometimes makes sense really to change also the grade to a P grade. Although the basic concept of the grade layers is the same idea behind. It's usually a little bit thinner or thicker, and sometimes it makes sense really to change then to steel grade. But coming back to the high temp alloy geometries, this is a medium grade, and you see already that's a very specific design with all these chip breaking elements in it. Also, the corner radius are optimized really for these kind of materials. The same if you look for the finishing geometry. Also, that is perfect optimized for high temp alloys, Inconels, titanium alloys, these kind of materials. The main markets we find for sure aerospace, yeah, power generation, where we have these challenges with high temperatures. Also automotive, if you think about turbochargers, stuff like that. Yeah. For sure, stainless materials you find nearly everywhere. Cobalt chrome materials, powdered materials, stainless base. There's a lot of arenas where these kind of materials are being used. Also, like automotive parts, you know, also a lot of medicine applications are aligned with these kind of materials. So those are a lot of challenges to be solved and can be solved with our solutions here. The next thing is the machining process itself. For sure, that's for you as a person who is already very experienced, very easy to understand that we have for sure a cast or a forged material. So we have to have a roughing process. Yeah? Use for sure a tougher grade, a strong protected edge. So RH geometry, stuff like that is the ideal combination. Then we have the medium steps really to come closer to the final shape of the workpiece. For sure, then we can go to a next step of hardness of the material. We can use really a higher speed and feed rates, because we don't need to react so much on uncertain, uncontrolled situations. And for sure, then the finishing process, where we can really make sure that the forces are going down. If you have thin-walled workpieces, then it's very important to react also on that. Yeah, I have taken also one example which might confuse you, because this is not really exact the solution I would show you before. It's not taking really MS geometry, because you know it's a forging scale. What we need to machine there, it's a nitronic material, so a nickel-based alloy. And you see we are using here a stainless geometry and coating, because of the very hard conditions here around, and this would be the first step really to remove this first level of material. For the next steps, you would go down then to the MS or to the FS geometry, and really to machine it in that way. And you see also we can succeed. It's just to think a little bit different, to see really that is a challenge of the material. It's very hard to understand sometimes that just if somebody's calling or is just looking in the catalog. So the complete picture of the application is always important. Yeah, also if we speak about really, if you already have a complaint from somewhere and the customer saying, well, I have somehow wear, you need to really understand which kind of wear you have, and there are a lot of things you can increase or you can work on. Yeah, if you have really these wear patterns like the crater wear, you can really easily understand you need to go down with the speed rate and can increase the feed rate. If you have deformation, that's usually coming from really the heat. So also heat is really to be understood always in these kind of applications. For sure, you can also go down with speed here, and also use a lower feed rate, and to go up with a harder grade to make sure that you have less plastic deformation in this case. And yeah, you have these scratches at the depth of cut. Very often you see that if you have a hard skin on the workpieces, then you see that very often. Then you might can move a little bit this kind of thing. Maybe you have the chance to first remove the hard skin to then use the second stage of insert. So maybe the production process needs to be changed somehow. But basically, if you want to go on with that insert, you need to go down with speed and feed. Yeah, and for sure you have the chipping topics. It's helpful to increase a bit the speed and go down with a grade, means to have a tougher one, because that is for sure the first wear you can see. And weather-wise is for sure the breakage. So the grade is too hard. So it's better to have a tougher grade, which gives you more reliability in the process. For sure, you have sometimes also build up edges, means material will stick on the insert, and therefore it's helpful really to increase the speed, really to make sure that you are faster than the material can set down on your insert. Going a little bit through grooving platforms, which follow for sure the same idea, but for sure have a complete different shape. We have on hand 3 different grooving platforms: WIDIA Manchester, WMT it's called, Top Groove, and WGC. And the WGC is pretty much ideal for this kind of stainless and high temp alloys. Why? First of all, for sure, everything is PVD coated. Second of all, we have an internal coolant system here included, which you can apply the coolant really through the holders and get you the coolant just below the insert, which is extremely helpful to really control the heat, especially on this kind of high temp alloys. So we have here a pretty much interesting product on hand where you can really improve your the applications. I will show you also the video. Sometimes I will jump a little bit through it because it will take overall 1 minute 51, but it shows basically all the benefits of this kind of product. Yeah. It's extremely versatile, so it's not only being used in high temp and stainless application. You can use it also for sure for steel applications, and that's very interesting. It's pretty universal, really, for grooving, for cutoff, and also for turning processes. So you can have a profiling with it only with one insert, which gives you a very high flexible usage of it. Very stable connection with 3 different shoulders on it. And it's very easy to select because the grades are very easy, and also the assortment of different geometries is very easy to handle. That is the most interesting feature of it, really, to have this internal coolant, which gives you really the coolant below the chip, and then you really can make sure that the heat is very controlled. Yeah, also one interesting thing, we made some lab testing also with that insert, because we wanted to know also how good that insert is, and just by using really this kind of new geometry, we can really increase the tool life from 50 to 73 passes, and that is pretty amazing, and gives you a lot of more productivity. Coming a bit to the hole making stuff, we are running a little bit out of time, so I have to speed up a little bit. For sure, we can use also solid carbide drills, and we have a special series also for stainless material with TDS 45 series. And for modular drills like our TDMX, we will launch here a geometry especially for high temp alloys and stainless materials in the April 1st. So that will come. Although the actual insert is also on martensitic and low alloyed stainless steel working pretty much good. So that's also not a stop here on these kind of applications, but let's focus a little bit on stainless steel and indexable drilling, because therefore the stainless is a very high challenge, because the concept of drilling, making this hole is very complex to understand. It's much different from the solid carbide and modular drills. So very important is to understand the material for sure, as we spoke already about it. The depth of cut is extremely important for these kind of drills. Diameter, the construction, stability, the environment, coolant pressure is extremely important, especially with stainless. For sure, the machine itself, tool holder and machine connection. Very often you come to these kind of problems, and especially in stainless, you have deflection, you have problems to control the chips, you have a bad surface quality, workpiece material is between hole and the tool itself, and that they need to understand how you're going to solve that. First of all, if you look at the forces you are creating with the tool, as it is supposed to be a one cutting edge tool with really unsymmetric forces what you put in the tool. This is the most challenging thing. So means in theory you just calculate with one cutting edge for the feed rate compared to two from a standard drill. That's a very challenging thing from the technology point of view, what we solve for sure today. But important is also to understand we create somehow a torque here in the tool, and the tool is pretty much bounded, because for sure this part is just steel, and you have carbide, and gives you also forces here in every direction, and every diameter and every length needs to have a different design of the pocket seat, because you need to calculate really the complete force directions to make really sure that everything has been in the right way. Just to understand how much challenging that all is, I want to show you what you are losing on the depth of cut in stability and stiffness of the tool holder, of the tool itself. So means if you have a length of 2 times D and you have 100% of stability, what you can use. If you go down up to a 5 times D tool with the same design, with the same inserts in it, you just lose more than 90% of your stability of your tool holder. And this is very crucial and very critical to understand that this kind of length is really a huge challenge for a tool like that. I know a lot of people think, well, it's not a big thing, easy inserts, they are cheap compared to maybe a drill with a full contact zone. But it is not. The secrets are really in the details, and therefore we also show a lot of recommendations which are shown in the catalogs, and trying to really to help you in the application. First of all, very important thing, and that is also a thing what I find very often in turning machines, is the coolant volume, and for sure also the pressure. But the volume is the most important thing, really, because you need to evacuate the chips, which is extremely challenging, because you have a 0 degree situation of the insert, and there's no natural movement of the chips out of the hole. That is the reason, if that is not working, that you really get problems with having chips around the tool in the hole. And therefore, a lot of recommendations are mentioned here, especially for the 4 and 5 times D. Please respect them, and it's really pays out in tool life and performance for an indexable drill. Also, I put in here some troubleshooting hints. How to understand that means if you really have problems and vibrations like you see here in that picture, you should follow these kind of 1, 2, and 3 hits. Means reduce feed, increase cutting speed, and increase coolant pressure. This is would be the solution for problems of vibration and really bad surface. If you have breakages here on the outside insert, then you should follow up, also reduce feed, check surface quality if not okay. Also look at that first. Use a tougher grade, but because maybe the vibrations are too strong, and maybe you can also increase the feed rate or can stabilize the higher feed rate with a 34 geometry. If we have the inside insert breaking like that, then you follow these kind of hints. 4 means check surface, 5 double check of the clamping of the tool, 6 workpiece maybe vibrating, and 7 maybe you can change to a tougher grade to it. The second point, if we have really chips between hole and tool, here in that area, you see that also in the pictures earlier, what we can do here, for sure increase feed, because really to make sure that we get thicker chips which are breaking easier. If it's really long chipping materials like high-temp alloy, also can be the solution decrease feed. So you need to play around with the machine to understand when the chips are breaking, because the breaking is really the challenging thing. Or we can also look at the coolant. That's very often the critical point, especially on high temps and really stainless materials, that the coolant volume is really low, and therefore we get heat up the material, and then the material going to be changed, going to be soft, and yeah, been taken not in the correct way. Long chips is always a challenge in these kind of materials. Increase feed rate, and you can maybe also use a geometry for a lower feed rate. Also, we have the situation really to use a V38 geometry. And for sure, too much wear at outside insert means you need to reduce the speed rate here. You can use for sure also a geometry which allows you to go a higher speed rate, and for sure also look at the coolant. I get here a question, that's a very interesting question. Diameter 26 3 times D in stainless steel, what is the best solution? What is better, indexable or modular? This is a question, you are in a situation, you need to understand first of all what kind of machine you have in front of you. That's a very crucial point. How much power do they have? Is it enough to have power to run a modular drill? If yes, I would go for a modular drill, because you are usually for diameter 26, you are faster. So productivity will be increased because you have 2 cutting edges. But if the situation is like the machine is not powerful enough, I mean, you might think about an indexable drill, because for sure the inserts are cheaper. So it's not an easy answer to give here at that point. So you need to look at the complete situation. This is a little bit about the Top Cut 4. We have basically 3 geometries, and the medium one, the V36, has also been available in an aluminium geometry. So also in an aluminium grade, so we can cover really a huge range of materials. But for stainless materials and high-temp alloys, the V36 and V38 are the ones which are the first choices, and you see it here in our overview from a bit different point of view. Here you find the V36 with M and S materials, and also V38 M and S materials. So it's also not really easy to sort that out, because it depends again on the length of the tool. If you do you have a 2x D or a 5x D, you have to look at that. Yeah. Just want to show you also a result. This is coming also from a customer from aerospace. Usually that's coming also from Israel. We can win here easily, really by just changing the tool and have just a double tool life. I mean, that's the easy thing you can do with a customer, and that was a pretty nice application. A second application I want to show you, that is the stainless part, which is done in Germany. That was against the Swedish competitor. I won't name it. But that's for extruder housings. This is a part of a sausage machine. So they produce sausage machines, and the sausage material needs to move to the extruder here, and that's a huge part. You know, that's a diameter 54. So it's pretty much easy to improve these kind of applications, because reliability is here the key for this kind of thing. Was very nice, so we can really dig in easily here. Yeah, generally speaking about the recommendation for hole making. First of all, indexable drilling, top cut 4, V36, 38. Think about really length of the hole. Do you need a long tool if the hole is not long? Please use always the shortest tool which can be applied. That is a very important thing. Also, the coolant is really key for success here. To control the heat is the most important thing in indexable drilling. If we look at the solid carbides, you know, we have the Vari drill and the TDS 4.5. The 4.5 is really the high performance tool for these kind of applications, but also Vari drill can be helpful in some applications, because it avoids really the contact to the wall, means it's not rubbing at the walls, so it's not creating a lot of heat, but the performance is usually a bit lower than compared to the TDS. And for sure, for the monolith drilling, I just recommend to you to wait till the 1st of April, because then we will launch in the new M geometry in the best grade, where you can really expect the highest performance on this kind of drilling. But that will be showed also in separate calls and separate trainings. Yeah, so far was that the topics I wanted to tell you. If you have really questions about more details, you can easily look at our website, widia.com, or use also our digital cutting tool assistant with Novo. We have also a nice technical contact where we really have a telephone hotline or a chat possibility, or you can send them an email really with technical questions. And for sure, yeah, if you would like to follow us on our social media activities, feel free really to do so. Also, for sure, if you need some videos on it, you can have a look really on YouTube. We have a WIDIA channel there, and a lot of videos are been shown there, and they are also helpful if you reach out to customers. And as I see there, we have also some distributor colleagues in here. Use them and show it to customers the performance, and that would be an easy argument really to support the sales activities. Yeah, from that point, I know we are a little bit over time. That was it from my side. I would hand over to Isabel now to have really questions and answers if necessary.
Yes, Mike, we have a couple of questions. So do you want to answer them, or we will answer them by email because I know we are a little late?
Yeah, some of these questions are answered already. We spoke already about the TP500 competitor grade, which was not a stainless thing.
Yes, there is one that I don't know if you answered, that was, how do we know whether it's positive or negative insert?
Well, it's dedicated to the situation. Usually, a customer is already using some inserts, and usually you're coming to the point that you need to optimize this kind of application. And from that point on, you start to investigate the application. First choice is always a double-sided insert, so a negative one. Because for sure you can expect to use it more times than a positive one. So that's the first point where you need to make a decision. If it's an inside machining operation, very often you need to use a positive one. So then you are forced to use these kind of insert. So it's most of the time it's really the choice by the customer already, and by the application what you need to do on the workpiece.
Okay, thank you, Mike. Yeah, I have another question. How many millimeters tolerance in Top Cut 4?
That's dedicated to the length of the tool. We are giving in our catalogs a table of it. So means for every size, dimension, on length, on diameter, we're giving the expected tolerance window, what we can achieve with an indexable drill. So it's not generally, a small diameter 12 2 times D will have a different tolerance than a diameter 68 5 times D. So that's for sure clear. But there's a table given, and that's been easily accessible through our website in the catalogs.
Yes, we will send you the catalog so you can check it out. So great, Mike. I think we don't have any more questions. If you have any, okay. Yes, because in my experience, Top Cut 4 diameter 20 3D result hole in diameter 19.6. This is the same person who was asking the question about tolerance.
Yeah, it can happen, but then we need to really dig deeper in the application. Maybe speed and feed needs to be adjusted. Maybe as a workpiece itself is having somehow a problem. Maybe clamping could be a reason. Maybe coolant can be also a reason. So it's not really just to be answered in one sentence here. It's a very important thing. Maybe we can take it offline if you can, please forward more information about the application to understand what's going on. Maybe the type of machine is important, the coolant pressure and volume, and then it's possible to dig a little bit deeper in that case.
Yes, we will contact you offline. So thank you for asking. So perfect. We don't have any more questions. I thank you for being here in this webinar, and we look forward to seeing you in the next. And as Mike said, follow us on our social media channels so we can stay connected, and we can also you can also see the latest news on our products and applications. And have a great day, evening, and see you next time.